The next step is going to be to attack some of these conservation of linear momentum problems. Your textbook goes through derivation of the principle of conservation of linear momentum. I'm going to skip all that and cut to the chase and write down the important equation, which is that the momentum of the system before a collision and the momentum of a system after a collision are equal to each other. So on the left-hand side of this equation, I have the total linear momentum final, that's what the subscript F refers to, and on the right-hand side, I have the total linear momentum initial, that I subscript means initial. The kinds of problems that you're going to deal with are generally going to be two-body problems, in which you have the two objects that are going to approach each other, and then those two objects are going to collide, and then you'll have the two objects going away from each other. So I'm going to sketch a diagram of that. So these two objects are approaching each other, and they're going to collide. After they collide, they're going to have some different direction and some different speed, perhaps. So here's how I could write the principle of conservation of linear momentum for this two-body system. This vector equation that has the masses and the velocities in it is probably going to be the most useful way that you're going to write the conservation of linear momentum. Sometimes the problems are going to be simple, in which you'll have a one-dimensional collision. They're going to be colliding in a line, and when that happens, then you only have to deal with one coordinate system, like the x coordinates or the y coordinates. In many cases, though, you'll have a two-dimensional collision. So you'll have some initial velocity that has an x and a y coordinate. You're going to have final velocities that have x and y coordinates. And this vector equation is going to break down into an x part and a y part, which we'll see when we work some example problems in a few minutes. One other detail that I want to bring up before we start solving numerical problems is to notice that there are two extreme types of collisions, and most collisions fall somewhere on a continuum between those two extremes. You have what are called completely inelastic collisions and completely elastic collisions. The more common type that we see in the everyday world are completely inelastic collisions. And in this collision, after the collision occurs, then the two objects stick together and move together as a single unit. So this might be two football players, a linebacker trying to tackle a runner, and the tackler hangs on to the running back and they move together as a single unit after a collision. Or maybe it's a couple of pieces of clay that stick together and move as a single unit. On the other hand, the other extreme are completely elastic collisions. In these, we say that kinetic energy is conserved. There is no lasting deformation that is done to the colliding objects. There's no damage that's done. There's no sound generated. There's no heat generated. And all the kinetic energy that was present in the beginning of the collision is present after the collision occurs. Completely elastic collisions are common on the atomic and nuclear scale, but in everyday life, these are uncommon types of collisions. Probably about as close as you can come are billiard balls that strike each other, but there's some sound that's generated in the billiard balls, so even those are not completely elastic. All other collisions are going to fall somewhere on this continuum. So when you think about a tennis racket colliding with a tennis ball, that's going to be somewhat elastic, so it would fall kind of on the right end of this continuum. On the other hand, when you have a bullet embedding into a block, that would be a completely inelastic collision. If the bullet bores through the block, then it's going to be kind of elastic because the two objects don't move together as a single unit after colliding. Realize that most collisions are going to be something other than completely elastic collisions unless the problem statement tells you that. So now let's get on to some problems. A 5 kilogram mass A, whose velocity is 2 meters per second to the right, collides with a 3 kilogram mass B, whose velocity is 2 meters per second to the left. The objects are moving along a frictionless surface. After they collide, mass B has a velocity of 2 meters per second to the right. Part A. What is the velocity of mass A after the collision? And Part B. Compare the total kinetic energy before the collision with the total kinetic energy after the collision. The first observation I want to make is that this is going to be a one-dimensional collision. And the way I know that is that mass B was moving in the x direction before the collision, and it's moving in the x direction after the collision. They tell me that in the way that they've worded the problem. And so I don't have to worry about sliding in the y direction at all if there was an xy plane. So I'm just going to work with x coordinates here, and I'm not even going to write the subscript x, but to recognize this is a one-dimensional problem. Let's sketch a before and after picture of what's going on. Frequently, a good diagram will help in a lot of these problems. You'll notice that I've put a negative sign with the initial velocity for B. I'm saying that to the right is positive and to the left is negative. You have to pay attention to the signs when you deal with linear momentum. Now let's draw the after collision, the after part. Now we want to figure out what is the velocity of object A after the collision. We're going to apply the principle of conservation of linear momentum. In its simplest form, it's written PF is equal to PI, where PF stands for the total linear momentum before the collision occurs. Part of that momentum's in object A, part of it's in object B. And on the right-hand side is the total linear momentum before the collision, the initial. It's going to be some of it in object A, some of it in object B. Now I want to rewrite this for my two objects that I have here. This equation is a vector equation. Even though I don't have any vector signs, I'm understanding that I can show the directions with a sign and that all of the direction is understood to be in the x direction. Now, I know everything in this equation except VA final. So let me solve that equation for VA final. And now let me substitute in the numbers. And I get that VA final is equal to negative 0.4 meters per second. In other words, object A is going to be moving to the left, and it's going to have a speed of 0.4 meters per second. To the left, negative 0.4 meters per second. Now we're looking to solve part B. We want to compare the total kinetic energy before the collision, part of it's in A, part of it's in B, with the total kinetic energy after the collision. So let's write down what the energy before is, what the energy after is, and then figure out what those numbers are. So the total initial kinetic energy is going to be equal to the initial kinetic energy of object A plus the initial kinetic energy of object B. And now I've written the kinetic energy in terms of mass and velocities, and I'll put in the numbers. Now, here's an important note. One of those velocities is going to be negative, but when I square the negative number, I'm going to get a positive number. So I'm never going to have a negative kinetic energy. Even though one object's moving to the left, it still has a positive kinetic energy. And now I'll put the numbers into my calculator and come up with the result. I've got 16 joules of kinetic energy before the collision occurs. Now, let's figure it out after. Again, we have that the total kinetic energy afterwards is going to be the kinetic energy from object B plus object A. So we've got two pieces that have kinetic energy after the collision is over. And again, we write the kinetic energy in terms of the mass and the velocity, and we feed in the numbers. And I get that the total kinetic energy after the collision is 6.4 joules. What happened to the kinetic energy? Well, it was transferred into other kinds of energy. Maybe there was some sound, maybe there was some heat, maybe there was some damage that was done to the carts in the form of work that did some bending. But the idea is that the total kinetic energy after the collision was not the same as it was before. So on this continuum, it is somewhere in the middle between a totally inelastic collision and a completely elastic collision. Now we're ready for the next problem.